Hello, thank you. Sorry, I'm going to the. I hope you can see my screen and
Yes.
hear me.
Yeah.
So I'll try to be quick. Um, as a motivation and context for this work, all of the previous speakers explained very well our motivation. So I will proceed these parts as we are running out of time. I will have here more detailed explanation of scientific features of Martin, but I will skip that. So in this presentation, we will focus more on the emulation part and real-time simulation layers of the Martin. So these are the two layers in the bottom, and the equipment that you already see from our lab that will support our simulations. So when we have our real-time target, this equipment here that is receiving many inputs and outputs that we can have from the layer of from the knowledge layer from our business models and decision support algorithms that we have. We will build a Simulink model regarding our network and the consumers and distributed generators components. So all the electric components and the elements of the grid should be built in the Simulink. So we have the interface part of the simulation and the simulation part. So the question here is that we will run this in the real time. So people usually working on the Simulink, they know that 1 second in the simulation can take several seconds in the real world, depending on the complexity of your model. But here we are fighting to have the simulation going exactly at the same time as reality is going. So for that, we have this specific special server. And also, we need to improve the specific Simulink models according to the emulation that we have in the lab. So as I said, in the machine, Simulink model is inside, but we are with the hardware in the loop concept, where we send signals to the emulated equipment in the lab, and we get on the loop the actual measurements, so we can validate and improve the Simulink models, but also the decisions that we took from several algorithms. I will focus on first on component modeling work that we have been doing in the last months. So we made a set of measurements in a load bank. In fact, this is this equipment here that is a load emulator with five different load banks inside, and with these different banks we can in each moment, in order to emulate a specific consumption profile that you can have, we can select what are the banks actually consuming, so we can emulate any level of load. Then for us to have in the Simulink a more accurate model of these each of these banks, or of the load in the end, we have applied to a power amplifier different signals coming from OPAL-RT target that I show. So in the method, we define first what are the voltage, amplitude, frequency, and phase angle that we will apply. That will change over time. So we test all the conditions that we want to validate our model. So we define the banks for this load are these 5, and then we run all the measurements, and after that we do the data treatment so we can define the model. So as I said, as we apply different power supply conditions, then we will have the load going stable in some time x, and then in the z time we are collecting from energy meter in each second the actual consumption. So in our this is the power hardware in the loop concept, because we are also changing the source, the power supply source characteristics, and our Simulink model step is 50 microsecond step. So the real measurements are taken, and the model is updated in each 50 microseconds. So this is very real time. So that's why this is quite complex, but this is the way that we found to make a realistic model for our load. And this is very important in the context of electrical grid operation, but also for the demand response impact and the distributed generation impact in this grid. So as I said, we have created several range of variation in each power supply parameters here in this table. So we have more than 6,000 scenarios, and this is just an example of the load that the voltage reference that we sent to the amplifier for him to feed the load. And we can see that this is a 3-phase load, and for each load the voltage amplitude is different. So this is an unbalanced voltage feeding. So this is the output that we are getting in the loop from the load. So we have the voltage and the currents, and this is what we get from the amplifier, but also we will have the measurements from the blue meter that I show. And after all the measurements that we are applying, those more than 6,000 scenarios, I am showing here all the measurements, and we are organizing each graph depending on the load, the load bank, each one of the 5 load banks, and we are testing to obtain, for example, here we have a linear regression of the equation that can represent the consumption points here. So in function of the voltage, the total voltage that we are applying from the source, this is the actual consumption of the load. So when we buy it, this is a 8 kilowatt load, but in fact this is just the rated power in the rated supply conditions, that which are not always or maybe never happening. So depending on the grid conditions, this is the real measurement that we will get, so we can have a more accurate value of the actual consumption depending on the actual voltage. So going to another example, this is from eco-rural IoT project. In this one, we were cooperating with a Spanish company that was working on the energy management. And also we had a pilot in a farm that we want to improve energy efficiency there, supported by IoT technology. So IoT was there to support all the measurements of evaporation, temperature, humidity, raining, and also energy monitoring. And there we have a PV panel and also a water tank that we can store some water. And then we have pumping of water to the tank from the river, and also the motors to pump the water to the irrigation system. From the energy supply side, we have also a synchronous generator that we can control, as we have a river running there, and we can generate electricity from a synchronous generator. So this is the decisions we take in each moment according to the PV and the demand we have for irrigation, of how much is the amount of synchronous generator that we will use, and also the equation and the parameters that we take to model the amount of water that you need in each moment where the irrigation system is working now. So I will not give many details on this. This is the equipment in the lab that we take to model the synchronous generator. So this induction motor is representing the water running in the river. And according to this speed of the water, let's say, we can increase the generation from the synchronous generator. And here on the right, we have the motor for both the irrigation and for the water pumping. And we are controlling by our real-time simulator according to the conditions that we have in the scenario inside. So this is a view on our lab where we have the real PV in the rooftop, and also the cables that are also represented in our lab. So this is these results are already published in a paper that I will show the reference. I think it also appeared previously. So this is the decision that we take in order to minimize the energy cost. So we have PV there. We have the synchronous generator. This we don't pay the energy from there, but there's a cost of operating it. And also we are buying electricity from the grid. And in some moments, if you have PV, you can, and for some reason you are not consuming all the PV, you can send electricity to the grid, and you have a revenue from that. So we have the maximum amount that you can use from each of these variables. So how much PV you have in each moment, how much is the synchronous generation available. In fact, PV you cannot dispatch, you will use what you have, but synchronous generator you can dispatch, but not always you have enough water in the river running, so you can use the full capacity of the synchronous generator. So this is the profile of the consumption that we need, and also the PV generation available. And these are the decisions that we take in one scenario for the irrigation motor and water pumping, and also according to the equation that I shown, what is the actual tank level. As we are running in a farm and we don't have a server there to support our linear programming optimization, that we put on RStudio. We want to make intelligent decision by rules, so we can make it in a programmable logic controller, a PLC, and also the same decisions we can take with an Arduino. So we need some rules if then else, if consumption, for example, after obtaining these three, this is an application like Professor Carlos Ramos explained, where we, according to the actual context parameters, if the consumption is more or less a certain amount, and if the market price is this or that, you can select in this hand we can select the maximum capacity of the synchronous generator, because electricity price is very expensive, and you have a lot of consumption and so on. And this is the tree we will obtain, and this is the set of rules that we encode to the Arduino and to the PLC. And we, of course, the decision tree is not very accurate, but it's what we get from what we want from the technical conditions we have in the farm. And here we can compare the actual decision taken from the optimization and from the decision tree. So for example, in this peak we have some little different, but it's something that we can handle. And also the actual dispatch of the generator, and the actual measurement that we get, because the generator cannot come from 0 to 2 kilowatt immediately. We need some ramping, and this is the actual measurement we have in the lab. So that's why it's very important that we work in the lab before we go to the real farm. And more references for other motors. And in the end, the actual energy coming from the grid compared to the total consumption. So as a little conclusions, we would highlight that real-time simulation is very important for us to validate our decision models before we go to the real field. I will not say real world, because we work in a real world. This is a real lab where we work, but the real field where commercial products are being used in a real farm in this case. So real-time simulation has been very important for us to validate our decisions before we go to our SME and other companies with their products. So with that, I would say thank you, and I hope to handle your questions.